Hello Math 1093, this is Dr. P with a video about exam question Q16, the one in which you were asked to solve two equations involving logarithms and exponents. Alright, so on this one I'm going to go through the solutions to both of them, but I should mention up front that people had generally pretty good success with part A and then usually somewhat less success with part B. But we're going to talk about some of the connections between these two types of problems, logarithmic equations and exponential equations. Alright. Really, the main connection between both of them is that both involve using logarithms in some way. In part A, we're going to use what we know about logarithms to combine these into one logarithm and then solve by translating into exponential form. In the second one, we have it in exponential form, but we're going to use logarithms to break down these exponentials and then use properties of logarithms to break down those logarithms even more. Alright, anyway, enough chit-chat. Let's get to work. Alright, part A. We're given that the base 2 logarithm of x minus 3 plus the base 2 logarithm of x minus 5 is equal to 3. Okay, now a lot of people understood that the sum of two logarithms is somehow associated with a product. But we need to be really precise in how we write this down. Like, we can't just write down x minus 3 times x minus 5 equals 3. That wouldn't be true. We do know that the sum of these two logarithms is the logarithm of the product of these two numbers, and that is still equal to 3 because I haven't done any transformation on the right side. I haven't changed the value of either side. I've just rewritten the left side in equivalent form. Okay, so these are equivalent, provided of course that x is a number such that both logarithms are defined. More on that in just a bit. Okay, anyway, so we now know that the logarithm base 2 of the product x minus 3, x minus 5 is equal to 3. And we can write that in exponential form by doing one of two things. Either we can recognize that this is the base, this 2 is the base, the value of the logarithm is an exponent, and then this thing here is a power. It is 2 to the third power. So I can write that. But if I don't know that cold, the other thing I can do is I can exponentiate each side to the base 2. And that's what I'll demonstrate here. Okay, if I know those numbers are the same, then 2 to each number should give me the same value. And because I have an exponential base 2 and a logarithm base 2, those two processes cancel each other out, and I'm left with x minus 3, x minus 5 is equal to 8. So now I have a quadratic that I can solve, but to solve it, I'm probably going to need to do a bit of simplifying first. Alright, so if I distribute that left side out, I get that, and that's equal to 8. So I get x squared minus 8x plus 15 is equal to 8, and then subtracting 8 from each side yields x squared minus 8x plus 7 equals 0. Thankfully, that thing will factor. That factors into x minus 1 times x minus 7 equals 0, and because the product of those two numbers has to be 0, one of the numbers has to be equal to 0, so x equals 1, or x equals 7. So I get possible solutions. Those possible solutions are x equals 1 and x equals 7. But wait, do they both work? Because remember I said earlier that this step here, this one, only works if I'm not violating some domain restriction. And there's a very real chance that in the process of solving this quadratic here, I may have come up with a solution that violates one of those domain restrictions. So I need to go back and check. Let's check that these solutions work. Alright, if x is 1, then I get log base 2 of 1 minus 3, and already I know that there's trouble, but I'll just write the whole thing anyway. No, this can't work. Logarithm base 2 of negative 2 is undefined. Too bad. So this is not a solution. Okay. So that will not work. What if x is 7? Will that work? Then I get log base 2 of 7 minus 3 plus log base 2 of 7 minus 5 equals 3. Alright, let's just put a little question mark there indicating that we are checking whether this is true. Let's say log base 2 of 7 minus 3, that's log base 2 of 4. And then here I got log base 2 of 2. Is that equal to 3? Well, log base 2 of 4 is 2 because 2 to the second power is 4. Log base 2 of 2 is 1 because 2 to the 1 power is 2, and that is equal to 3. So yay, that checks out. Okay, so x equals 7 is a solution, and in fact it is the only solution the solution set is just plain 7, nothing else to it. Okay, so remember, I've always got to do that check at the end of solving a logarithmic equation to make sure that none of my solutions violate domain restrictions for the original equation. If they do violate, well, that's fine. That's not the end of the world, but that means that that solution, it ain't really a solution. So I've got to throw it out. And I have to see that happen. I have to see that reasoning going on. Okay, let's do the other one, part B. All right, this one's a little bit more intricate. Part B says, okay, 3 to the 5x is equal to 7 to the x minus 3. Okay, some of you tried rewriting these so that they have the same base. That's not going to work very well. I could make them have the same base, and there's a process for that. Like I could say, well, let's let 7 to the a equal 3, and that means the a needs to be log base 7 of 3. So then I could say, well, 7 to the log base 7 of 3, that's equal to 3. And I could rewrite this equation as 3 to the 5x equals, let's see. Actually, let me rewrite that a little bit differently because I really wrote 3 as a power of 7 here. Okay, so I could rewrite 7 to the log base 7 of 3. All of that to the 5x equals 7 to the x minus 3. And then that gives me 7 to the 5x times log base 7 of 3 equals 7 to the x minus 3. And then, because my bases are the same, I can match exponents and get 5x times log base 7 of 3 equals x minus 3, and then I could solve for x. Because that's a linear equation. But I also know that most of you are not going to prefer this approach, so I'll show the other approach, which is, okay, so this approach was, I'll just call that approach 1. Rewrite so that both sides have the same base. And it's always good to look for opportunities to do that. Sometimes that can work, same base. There we go. Like if this had been a 9 rather than a 7, then we're in hog heaven here. That 9 would be equal to 3 squared, and then I could simplify the right side and then use the fact that the bases are the same and get a nice easy linear equation. But in this case, 3 and 7, those numbers just don't have a whole lot to do with each other. All right, so let's try this a little bit differently. All right, one thing to know is that if I have exponential functions and would rather not have exponential functions, because, heck, these x's are sort of locked inside the exponents here, one way of getting rid of exponentials is to take a logarithm of each side. Which logarithm is up to you? I tend to prefer the natural logarithm. It's easy to write, for one thing. It's just 2 letters rather than 3 letters. And I don't have to write the base. The base is just built into the fact this is natural log. And that's what most people seem to start out with, so let's start there. All right, now the thing is I have to know some properties of logs in order to work with this. For example, I need to know that the logarithm of a power is the same as the exponent times the natural log of the base. And I also need to understand that that exponent, that entire exponent, is getting multiplied by the natural log of 7. And then I have to recognize something very important about this. This is a linear equation. It's gross, but it is linear, no doubt about it. Every term of this equation is either x times some number, like x times 5 natural log of 3, or it's a constant. So over here I have natural log of 7 times x minus 3 times natural log of 7, which means I can gather up all the terms that involve x by subtracting and I'm left with 3 natural log of 7 over here. Now I noticed some kind of funny business going on with the combining like terms. One thing to realize is that, for example, some people wanted to subtract x from both sides and get rid of this and then make that a 4x. Can't do that. Sorry. That's because this x here is not just plain x. It's x being multiplied by natural log of 7. And then the 5x over here is not just plain 5x. It's 5x times natural log of 3. And those two numbers, there's no easily known relationship between them, which means there's no like terms there that I can combine. However, I do know that this is x times this number, this is x times this number, and I can factor that x out, which is kind of like combining like terms. In fact, it's really the same idea. That's just a fancy way of combining like terms. When the numbers are not especially pretty, and believe me, it doesn't get a lot uglier than 5 log 3 minus log 7. Anyway, now I have a constant times x is equal to negative 3 log 7. I can finish this by dividing each side by this constant. So let's go. X is negative 3 natural log 7 over 5 natural log 3 minus natural log 7. And then I am pretty much done. I could go back and check that this works. But in this case, there's no reason for this not to work. Every step that I did, at least in this approach, every step that I did is something that could be reversed and something that is not going to run into any domain restrictions. The reason for that is these natural logs, they're being taken of numbers that are already going to be positive because 3 to any power is positive, 7 to any power is positive. So I'm not in any risk of running afoul of a domain restriction. So I can pretty much take this to the bank. It will work. The process of subbing it in and checking the equation works. A little bit torturous probably, but it could be done. There's no reason you couldn't do it. It's just a little bit gross. Anyway, so that's the process for solving one of these. The idea is start with a logarithm. Make sure you're applying that logarithm to both sides and to the entire side. So none of this natural log of 7 and then leave the exponent intact or anything. Got to take the natural log of the entire thing. Okay, and then use this power property of logarithms to unpack that and get a linear equation. And then just behave the same way you do around any linear equation, except this time the numbers are god-awful. All right, that's it. This will be the last video on exam questions, so hope that you had time to watch a few of these and learn something from the experience.